All right, this is Unofficial Advent of Code, day 22. Here we go. Reactor Reboot. Overload the submarine's reactor. Reactor core is made up of a large three-dimensional grid entirely of cubes, one cube per integer three-dimensional coordinate. Each cube can either be on or off. Could it be an old model of the reactor you've seen before? Okay, that's from last year. To reboot the reactor, you just need to set all of the cubes to either on or off by following a list of reboot steps. Your puzzle input. Holy cow. Cuboid, set of all cubes that have coordinates which fall within ranges. Oh, last steps are fully outside the initialization procedure. Oh, ignore 50 through 50. So this is 100 times 100 times 100, 1,000,000 cubes. Okay. Cubes equals false times all right, stirs dot each do command instruction chords equals command dot split core x chords xc xc yc zc equals chords dot split dot map to chord range range equals range range dot split dot map to I. Okay, and then all right, so xc0 xc1 that each do x xy next if x next if xc1 is less than -50. Next if xc0 is greater than 50. xc, yc, zc dot each to c. C0 equals -50 dot max. Min. Puts if C1 is less than 50 or if C0 is greater than 50, out of range equals true. Out of range equals false. Next if out of range. Sx equals x times equals y times 101. I equals sx plus sy plus z. New val equals chord equals inst equals on. Cubes I equals new val. Puts processing. Puts part 1 skipping unexpected end of input. Cubes dot count got it. 927. Okay. Run all of the reboot steps for all cubes in the reactor. Okay. So Oh, let's do this. Min x, x min, x max, x min equals xc. Okay. Cube ranges equals cube ranges x min, x max, y min, y max, z min, z max. Equals false. Command then let's see. Cube ranges dot each do. New ranges equals that. Range if cuboids intersect cuboid states cuboid states state cuboid state new val if cuboids intersect cuboid set cuboid equals xc. New cuboid states if cuboids intersect set cuboid and if state not equal new state. else. So we can basically always new cuboid states set cuboid equals new state. Cuboid states equals new cuboid states. Otherwise, new cuboid states cuboid equals state. So if the state, oh. So if they intersect, we're going to have to break up both cuboids. We're going to have to break up parts equals break up cuboid. Cuboid set cuboid. Parts dot each do part new cuboid states part equals state. So we're basically going to take our cuboid, get rid of the thing in the new cuboid, and then yeah. And that'll break it up into a bunch of parts, because you can imagine if imagine you have a big cuboid and then you set something just in the middle, then it's then that creates 27 different cuboids, and you can set those all to be something. Definitely there are more optimal ways to do it. You could probably do everything above, everything below, and then 4 cuboids around, rather than 26 different ones, but that's too hard to figure out. So we'll break it up, and then we'll set each of the parts to be the previous state. Otherwise, if they don't intersect, we'll just set them to the current state, and then we'll basically wipe over everything with the new cuboid, with a set cuboid. So def cuboids intersect C1, C2, and then def break up cuboid, cuboid remove. So we have wow, I definitely have drawn out this diagram before. So there are different possibilities. All right, so 6 possibilities. c1.zip c2 dot all what are we doing here? If for all of the ranges here none of them I1, I2, I1 min, I1 min, I2 max equals I1. They intersect so if none of the coordinates don't intersect, so if R1 max is less than R2 min, or R1 min or R2 max is less than R1 min. Def ranges overlap. Return false if R1 max is less than R2 min. Return false if R2 R1 min if R2 max is less than R1 min. True. All ranges overlap. Okay, so now we need to break up a cuboid. R1, so we know that they overlap. Okay, so let's do this. So if we have something like this that cuts off a corner, if we have something like this that cuts off the top, something like this breaks it up into 6 pieces. So there's basically a before and an after, a before, a middle, and an after is the general idea. But some of those might be empty. So cuboid.zip minus .map do C range M range dim ranges so let's see. CR min, C min, C max, M min, M max equals M range. Okay. What if we have something like this? In the X direction, in the horizontal direction, all right, how do I do this? do. So when I have this, and I chop off that. Oh, maybe I can basically just break it up into oh, that's how I do it. So I have this is the thing that I want to remove. And so I can basically iterate over I can iterate over like this section to the top left of the to remove, above the remove, to the top right of the remove, to the left of the remove, within the remove. I skipped the when it's inside of it. To the right of the remove, to the left, below, and after. So before, left, left, overlap, right, dot each do X select X. So Cx equals cuboid 0, Mx equals minus 1. So when we're doing like the selecting to the right of the X, we're basically going the max plus 1 def intersect range R1, R2, return nil if ranges overlap. Do 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 do. How do you get the intersection? Basically, do you just take the min of the mins, the max of the mins, and the mins of the maxes? The max of the mins. And the mins of the maxes. Return nil if ranges overlap. If they do not overlap. Okay. So, parts equals this. X intersection def side of range. So range selection case selection when left, then number n infinity equals x min, y min, y z min dot min minus 1. Then n infinity range 0 minus 1 when overlap, then range, when right, then range. Okay. X intersection equals intersect range of cuboid side of range minus next if no X intersection select Y X intersection Y intersection Z intersection parts. Next, if select X next if select X and select Y equals overlap and select Z equals overlap. Puts add cuboid cuboid.inspect puts removed puts got part dot inspect. Parts dot empty. Got nothing. Okay. Let's do this. For simplicity, let's do YR equals 0, 0. YR equals Y min, Y max. So we have oh, oops. There we go. So we're just looking at the X. We go through, so we have 95002 to negative 26, and then 23 to what comes after. New cuboid state 188. So 566 to 77. So this is 74038. Perfect. 774 to 87 minus 74 to 92. Got nothing. Perfect. 9012 to negative 72 minus negative 7. So this is negative 7. All right. Perfect. Now let's see what we got. Let's look at some smaller numbers, please. Break. So this should give us, this is a 2D range, and yeah, basically everything except yeah, okay, I think it's working. So now we want to do total on equals 0, cuboid states dot each do cuboid state. Next, if not state, size equals cuboid 1 cuboid dot each do LR size times equals R minus L plus 1 size total on plus size puts part 2 total on. Woohoo! Let's go. Do 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 do. Yes. Day 22. 43 minutes. Oh, I was pretty close. 5:53. I don't think I was close on that. But I don't know. I did all right. Okay. Let's talk about it. Reactor Reboot. Operating at these extreme ocean depths has overloaded the submarine's reactor. It needs to be rebooted. Reactor core is made up of a large three-dimensional grid made up entirely of cubes, 1 cube per integer three-dimensional coordinate. Each cube can either be on or off. At the start of the reboot process, they are all off. To reboot the reactor, you just need to set all the cubes to either on or off by following a list of reboot steps. Each step specifies a cuboid, set of all cubes that have coordinates which fall within ranges for x, y, and z, and whether to turn all of the cubes in that cuboid on or off. So we set everything between 10 and 12 for each 3 coordinates to on, everything from 11 to 13 on, whatever. Then it turns some things that off. So we turn things on and off. Initialization procedure only uses cubes that have x, y, and z between -50 and 50. So we go through the steps, how many cubes are turned on. So -50 and 50 is 101 spaces. So we're just gonna have an array with 1,000,000 spots, and we're gonna initialize them all to false. And we'll go over all of the strings, get the ranges. For part 2, we're gonna I need like the min and max ranges. So I just update those here for part 2. So now we wanna know whether this is out of the initialization range. So if the right side of the range is less than -50, or if the left side of the range is greater than 50, it's out of range. Then we clamp it to within -50, 50. If it's out of range, we skip it. And the new value is if the instruction is turn them on, then it's going to be true. Otherwise, it's going to be false. And so then we just loop over all of the x, y's, and z's. We multiply the x coordinate by 101 twice, the y coordinate by 101 once. And then we take the z coordinate, and that maps every x, y, and z to a unique index. And then we just set the new value, and then we just count how many things are true. And that is part 1. So then for part 2, basically we need to reboot the reactor, and we need to do the same thing, but for all of the cubes, not just the ones in that range. And so, yeah, that's complicated. So the way that we're going to do this is basically, instead of having these numbers are like in the 10,000s, in the 100,000s, so instead of having like 200,000 cubed different values, there's no possible way to like loop over all of those. We're basically going to like keep track of contiguous regions that all have the same value. So we get the lowest value that we see and the highest value that we see. And to start with, everything, we have a state. This is the states of different cuboids. And initially we have one cuboid, which is from the x min to the x max, y min, y max, z min to z max, and that's false. Everything in there is false. So then we're going to go over each command, get the ranges, and then we have the cuboid that we need to set. And then we're going to build up a new set of cuboid states, and we're going to set those things to, on or off. And the idea here is that for each cuboid state, for each cuboid that we already have, if that intersects with the new the cuboid that we're setting, we're going to break up the cuboid that everything was the same. We're going to break it up into as many cuboids as we need by removing the part of it that is getting set. And then for each of those parts, we will say that that part is in that state. Otherwise, if they don't intersect, we can just leave it as is, and we say, hey, everything in that original cuboid is in that state. And then, basically, once we've like subtracted the set cuboid from all of the other cuboids, all of the things in new cuboid states, none of those cuboids overlap with the set cuboid, the cuboid that we're setting. And so then we can say the setting cuboid is equal to the new state, and then we update all of our states for the next iteration. So the key things here are cuboids intersect and then breaking up the cuboid. So to check if two cuboids intersect, we basically want to check if, so these are like different ranges, different ways for things to overlap. And so we're going to check if two cuboids intersect, then for all of their dimensions, their ranges overlap with each other. So to check if two ranges overlap, we basically break up our two ranges. If we look at, this is basically all the cases where like the start, there are like three parts. There's the left, the middle, and the right. And so if you start, and your start and end can be in any of those three states. So you can start, this is like start left and end left. This is start left and middle, start left and right, start end middle, start middle and right. And this is start right and end right. So only these middle four all actually do overlap, but the first and the last do not. So we break up the ranges. If the max of the first range is less than the min of the second, they don't overlap. Or if the max of the second is less than the min of the first, they also don't overlap. Otherwise, they do. So that's how we can check if the cuboids intersect. Then what we want to do is we want to break up a cuboid. So the way that we do this is we basically imagine that we take the cuboid that we're subtracting and imagine that we can break up the world into 27 different cuboids. We take the 8 corners of that cuboid and we take above, like we take left within the cuboid right, we take in front with the cuboid behind, and then above with the cuboid and below. So that gives us 27 different cuboids, and the middle cuboid is the actual cuboid itself, and then all of the other ones basically like start on one side and then go off to infinity. So we're going to say there are these three like sides, left, this is the left, this is overlapping, and then this is to the right. So we're going to loop over, so we can take the cuboid that we want to remove and break the world up into 27 different cuboids. And then the other cuboid that we have just lives somewhere else. And we're basically going to take the intersection of that like part of the cuboid with the cuboid that we have. yeah, I don't know if that really makes sense. So we basically say like, we loop over left overlap right for each dimension. And then we're going to get the side of the range for that dimension, which is up here. So if it's left, it's from negative infinity to the left value, the min value -1. If it's overlap, it's the range itself. If it's the right side, it's 1 plus the right edge and everything up until infinity. And then we're going to intersect that with the cuboid that we want to like break up. So the way that we intersect things is basically if they don't overlap, there's no intersection. But otherwise, if you look here, like this is the overlap for this line. This is the overlap for this line. You can work it out that basically like you take the maxes of the mins. Yeah, because if you look at the two mins, anything less than the max is not, if you look at like the two left sides, anything less than the max is not in the other one, the max of the mins. So you get rid of that, but then everything to the right of that, at least until one of the ends is in there. So basically you take the max of the mins is the left side and the mins of the maxes is the right side. And so that's what you get when you intersect the range. So you intersect the cuboid that you want to break up with like this side of the range of the cuboid that you're subtracting. If there's no intersection, you're done. You just skip it. Once you have all your intersections, first of all, if all of your things are overlapping, then that means that like you're actually looking at the cuboid that you're removing itself. So if there's any intersection there, you don't want that bit. So we skip that. But otherwise, we take all of those intersection ranges and add that to a part. And so that gives us, that breaks up the cuboid into different parts. Yeah. So then once we break it up, loop over all of them, say they're in that new state, and yeah, it works. That's it. It takes a little bit, but not too bad. Yeah. Does it? What did I get rid of? This is longer than it took before. Oh, okay, no, we're good. Woohoo! So that is Advent of Code, day 22. Yep.